All right, hello everyone. Welcome to the first day of our general AP review. Over the next couple weeks, we'll be going over specific topics that were in our course this year, and that we need to be ready for at the end of your exam. I've chosen the topics to focus more specifically on the things that we need to work on based off of what I've seen in class. Some of it may appear redundant. That's in part the point, to make sure that you're keeping track and keeping in mind the things that are most crucial in terms of your learning growth. As you work through these packets, there's kind of two ways you can do it. You could treat it like a normal lesson. As I walk through it and indicate what you need to do, you take notes, pause, practice, check work, that kind of thing. If you're feeling like you're really good on some topic and you need to move faster, then feel free to go ahead and do your work and then come back and just use the video to check your work. I want this to be flexible and allow you to kind of do the kind of learning you want to do. But I do just want to make sure that you do spend time checking your work and getting your questions answered with this video. Okay? Let's go ahead and jump in and get started. We're going to be looking at limits and continuity today. All right. A couple reminders, big ideas from limits and continuity that we need to recall. Definitions are always important, so let's go ahead and rewrite down our definition of a limit. Definition we need to remember is that if the limit as x approaches some value, we'll call it c from the left, of some function equals the limit as x approaches c from the right of that function, then the overall limit, the limit we say as x approaches c of f of x exists. Ooh, if I can spell that right. Exists. Right. That's our fundamental definition of a limit that we need to remember. And what that means graphically is that if we're looking at some function f of x, whatever it looks like, for the limit to exist at point C, our value from the left side has to approach the value from the right-hand side. We actually don't care what is going on at that spot C. So the limit would exist here. In this case, our limit would be 3. So for this problem, the limit as x approaches C of our function f of x equals 3. For limit not to exist, we need to see a situation where at C, our function f of x, I'll call this one a new one. Let's say our function g of x. In this case down here, at that value, we need to have our function from the left side and our right side approaching different values. All right, down here, our limit from the left would approach 2. Up here, from the right, it would approach 4. So we can say here that the limit as x approaches c of g of x does not exist. All right. In continuity land, or at least in describing and thinking about continuity, there are 3 important things you have to check. And if you see these on questions, we need to list it out. 1, we need to make sure that the limit as x approaches c of f of x exists. That is relatively easy to check, just like we did over here, right? We need to make sure the limit exists, so you do those things in our limit definition. 2, we need to make sure that f of c exists. All right? And 3, we need to make sure that the limit as x approaches c of f of x equals f of c. If this is true, f of x is continuous at x equals c. So what do each of those things mean? Well, number 1 in our criteria means that the limit exists, so the left side and the right side have to be coming together. All right. For limits, we could have a hole there, but continuity says the point has to exist, so we have to have a point here at C somewhere, and the limit has to equal where that point is, so the point essentially has to sit right there in the middle and fill in any gaps. And then our function would be continuous at C. F of C exists, the limit from the left and the right side are coming together, the limit equals the point, so we're all good. This is to avoid situations, for example, where you might have some limit that exists and a point that exists, but the point does not actually sit where the limit is, and you end up still with a jump discontinuity there. This would not be continuous. All right. What I want you to do is pause and take some time to answer each of these, evaluate each of these limits or function statements based off of the graph of f of x there. Go ahead and pause the video and give that a shot. All right, let's roll through it real quick. Limit as -1, as x approaches -1 from the left-hand side is 2. Because that is what our graph from the left-hand side is. We track in. If you want to, I like to think about it as having like a vertical line here. As we approach x equals -1 from the left, our y value approaches 2. Right, how about approaching -1 from the right? From the right, approaching that x value, we end up at a value of 4. What about approaching -1 overall? Well, since the left and the right-hand functions, or sorry, right and left-hand limits are not equal, then the overall limit does not exist. Let's not say equals does not exist. Let's just say does not exist. I put a little arrow there. As x approaches, that should just say 0 from the left. 0 from the left approaches a value of 3. 0 from the right, coming from the right toward an x value of 0, we also have a value of 3. So what does that mean overall? Oh, we asked about the overall one? We're not. So there we go. Overall, the limit would exist though, right? Limit as x approaches 1 from the left. Limit as x approaches 1 from the left, coming at 1, has a value of 2. Approaching 1 from the right, coming into an x value of 1 from the right, has a value of 2. So what about our limit overall at negative? Or so that should say +1. I'm sorry. A +1. I'll fix that before I post things. I'll fix both of these before we post things. As x approaches +1 from the right, then since the left and the right hand limits are the same, then our limit overall is also 2. What is f of -1? At -1, our value is up there at 4. What is f of 1? F of 1 at f of 1, our value is also at 4. What is f of 0? F of 0 has a value at 3. F of 4, 1, 2, 3, 4, has a value at 3. X, limit as x approaches -2 of f of x. -2 is out here. The left and the right hand side do look like they're coming together at a value of +1. All right. So there's how we evaluate limits from a graph. Just as a quick review. All right. I want you now to practice. There are 1, 2, 3 multiple choice questions I want you to practice now related to limits. Go ahead, pause the video, and give those a shot. All right. So we can evaluate limits. We have several methods that we talked about earlier this year to do that. We said that typically the first thing we want to try, if we can, is plug in the limit value that we're approaching. So in this case, x equals 3. And if we plug that in, what we would get 9 plus 18 minus 27. So that gives us 0 over 0. So this would give us 0 over 0 if we evaluated it. Now, we'll talk about L'Hopital's rule later. This might cue you immediately to use L'Hopital's rule, which is fine. You could do L'Hopital's rule and get to the answer here. We'll show that in a second. Or we can factor, cancel out, and try our limit again. So the limit as x approaches 3. The top part factors into x minus 3. X minus... Ooh, what did I do? Sorry. X minus 3, x plus 9, sorry, over x minus 3. So there are factors. And we notice we have an x minus 3. We have a hole in here that we can get rid of. And then we can say the limit as x approaches 3 of x plus 9, which will give us 12. If you use L'Hopital's rule, sort of our general symbol, you have to show that the limit would evaluate to 0 over 0. Then we could say, okay, we're going to use L'Hopital's rule and then take the limit as x approaches 3. We take the derivative of the top, which will give us 2x plus 6, divided by the derivative of the bottom, which is 1. We plug in 3, that gives us 6 plus 6, which will also give us 12. All right. For label number 21, we have an infinite limit now. So if we want to, we could plug in, quote unquote, again. As x goes to infinity, we'd find that this goes to infinity over infinity. So if we want to, we could also use L'Hopital's rule and keep doing that until we get some value that works. Or we can do what maybe ultimately the quicker thing, which is to do our in-behavior model. Our in-behavior model says, hey, let me identify what grows fastest, what gets biggest as x goes to infinity. And in this case, our in-behavior model would follow, well, up top, x squared is going to outgrow everything else. And the denominator, x cubed, is going to outgrow everything else. And so we get that our in-behavior model kind of reduces down to following the same behavior as the function 1 over x, which has a limit of 0. All right, 23. This time we have a limit going off to negative infinity. We can use our same sort of pattern above. We could plug in, quote unquote, as x goes to infinity. We'd find another sort of L'Hopital's rule situation going off to plus or minus infinity things over infinity things. Or we can use our in-behavior model. I'll show that one here. Our in-behavior model would say, okay, this limit is actually going to be equal to the limit as x approaches negative infinity of what's going to dominate up top as x grows, 6x cubed will, over what's going to dominate down here, minus, we got to keep the minus sign, okay, got to keep my sign, minus 7x squared. Subtracting whatever that value is going to dominate underneath. So this leads us to the limit as x approaches negative infinity. When I kind of reduce my in-behavior model, I would get negative 6 over 7, or negative 6/7 x, right? As x goes to negative infinity, this will become positive, so this will go off to positive infinity. Okay. Notice I use arrows here a lot. If you want to avoid the accidentally making an error by saying something's equal that's not really equal, because nothing's really equal to infinity, you can use little arrows to avoid any confusion there. Okay. Moving on over. All right. Let's do this one together. Given g of x is this piecewise function, determine the limit as x approaches 3 of g of x, or explain why it does not exist. Okay. All I'm asked about is the limit here, and I'm asked about the limit as x approaches 3. And I see that on the left side of 3, I follow 2 minus x, and on the right side of 3, I follow 3x. I know my definition of a limit is if the limit as x approaches 3 of g of x exists, the limit as x approaches 3 from the left of g of x has to equal the limit as x approaches 3 from the right of g of x, right? So I can check that pretty quickly. The limit as x approaches 3 from the left, so the limit as x approaches 3 from the left of f of x would be the function 2 minus x, which would be as x approaches 3. X is getting closer and closer to 3 is going to take us to negative 1. And I could check the right-hand side, the limit as x approaches 3 from the right of 3x, because that's the right-hand side of 3. That's going to give me 9. And so what I just find, hey, the limit from the left and the right are not equal. And I can say then that the limit as x approaches 3 of g of x does not exist because the limit as x approaches 3 from the left of g of x does not equal the limit as x approaches 3 from the right of g of x. And whenever you're answering free response questions, we need to use all of our limit notation properly. You have to write this out. We can't just put sort of like fudge it in words. We need to make sure we understand the mathematical notation symbols here. So this is what you need to write out. If it helps you in processing, we could also do what maybe you remember from class, which say, hey, we can just check to make sure the left and the right-hand side are going to come together, essentially that they're going to be equal to each other at x equals 3 could be a little shortcut, and you would still find, hey, negative 1 does not equal 9, but you still need to make your conclusion down here stated out in limit fashion. Okay? All right. There are, just as a reminder, some limits we need to memorize, okay? We must memorize a few things. One, we need to memorize and just remember the limit as x approaches 0 of sine of x over x is 1. If you want to add that to the blue sheet that has all the AB or all the BC calculus things to remember, please feel free to write that on there. We need to remember this because it's a hard one to sort of get graphically unless you have a calculator. So here it is. We can also show that this is true using L'Hopital's rule if you would like. And then question 2. Down here, the other limit, we need to remember that the limit as x approaches 0, the absolute value of x over x, or x over absolute value of x, that's a mistake. I'll correct that in my corrections for you all. The limit does not exist. So in the actual PDF, I'll have this corrected. Sorry about that. Does not exist. Why? Because as x approaches 0 from the left, so negative numbers go to -1, positive numbers come to +1. We have a big jump discontinuity. Okay. All right. Now we can extend this knowledge in a couple of different ways. We could look at this and say, hey, the limit as x approaches 0 of sine of 3x over x. Well, if we plug in 0, we get sine of 0 over 0. So this is a candidate for L'Hopital's rule. So let's talk about that. Again, L'Hopital's rule says, if you have a limit that you're trying to evaluate of like some rational thing, and it gives you 0 over 0 or plus or minus infinity over infinity stuff, and some other possibilities, but for now this is what we'll use, then the limit as x approaches a of f of x over g of x is going to be equal to the limit as x approaches a of, if we take the derivative of the top and the derivative of the bottom and try that limit again. It's not quotient rule, we just take literally the derivative of the numerator, derivative of the denominator. So we got 0 over 0 here, and if you're using L'Hopital's rule, you need to show, okay, I tried this and I got 0 over 0. So using L'Hopital's rule, the derivative of sine of 3x, I need to keep my limits. You're going to lose points if you don't keep your limits. The derivative of sine of 3x is 3 cosine of 3x over derivative of x is 1, plug in 0, cosine of 0 is 1, so this gives us 3. Now, if we wanted to, we could have used some other manipulation. We could have said the limit as x approaches 0 of sine of 3x over x, is equal to, well, as long as I multiply by 1, I can keep this the same and kind of manipulate this kind of creatively. So I could say the limit as x approaches 0 of, let me multiply the top and bottom by 3. This will give me 3 sine of 3x over 3x. And notice now that what's inside the sine and what's down here are the same. And I know that the limit as x approaches 0 of the sine of x, and that x can be anything, the sine of whatever over whatever, is 1. Notice I have 3x, so that will become 1 times 3, which give me 3, the same thing. L'Hopital's rule at this point is probably a quicker and easier thing to do in a lot of these. Let's try this one. For any of these that we can use L'Hopital's rule, we will. I'm going to flag some other methods too. Sine of x over x squared minus 2x. If I plug in 0, I get 0 over 0 again. So I've got to write that out. I got 0 over 0. I'm going to use L'Hopital's rule and say that is the limit as x approaches 0 of the derivative of sine, which is cosine of x, over the derivative down here is going to give me 2x minus 2. When I plug in 0, I get 1 over negative 2, so I get negative half. All right. Another thing you could have done here is we could have factored out an x and realized, oh, we have a sine of x over x, so that will go to 1, and then I'll have a 1 over x minus 2, which will give me the same thing. All right, here, sine of x minus 2 over x minus 2, the limit as x approaches 0. Now don't be tempted. We do have here then the sine of x minus 2 over x minus 2. It's not sine of x over x. then x is going to 0, so let's try plugging in. This will just give me the sine of -2 over -2. That's fine. I don't have any problems with that. Okay. Let's try this one. We have x plus 3 over x plus, absolute value of x plus 3 over x plus 3. The limit as x goes to 0. Let me try plugging in. That would give me 3 over 3, which is 1. So I have no problems there. What would cause problems in these cases, though, is, okay, we're kind of shifting the limit we saw above, the limit I told you to memorize. We're kind of shifting this limit with x plus 3. We're kind of shifting it, right? Translating it. If this limit had been the limit as x approaches -3 of absolute value of x plus 3 over x plus 3, then this would have been does not exist, because now we're at that breaking point where this function would break. Okay. Okay. A couple reminders about some key vocabulary words here. Let's talk about horizontal asymptotes for a second. Let's remember, when we see the phrase horizontal asymptotes, what we're really looking at is what's called the end behavior, which we can find by asking ourselves about two limits, and you have to ask both limits as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x, because we have to check both ends of the graph. Sometimes, and in a good number of functions, those are actually like the same value, especially for rational functions, but not all functions are the limits in both directions the same value, so do check both of them. What are vertical asymptotes? Our vertical asymptotes are places, we can kind of think about it this way as a shortcut. If we have some function that's a rational function, f of x over g of x, our vertical asymptotes are where g of x only is 0. So the denominator only is 0. What are our removable discontinuities? Removable discontinuities, so when I say where, I mean x values. Removable discontinuities are what we call holes. That is where in a rational function, removable discontinuities are where, the x values where, f of x and g of x equals 0. So they have the same value there, so we call them removable discontinuity because we can, like we've seen above, like factor some stuff and get rid of just that one troublesome x value discontinuity. Okay? So what I'd like you to try now is, looking at this function down here, can you identify what are the horizontal asymptotes, what are the vertical asymptotes, and what are the removable discontinuities down here? Okay? Just one function to do. All right, here we go. Let's take a look. Let's start with the horizontal asymptotes. For our horizontal asymptotes, remember we said we need to check two limits. Limit as x approaches infinity of this function. It's a little hard to tell, though, as for these infinite limits from this factored form. So let me figure out what the non-factored form would give us in terms of end behavior model. What would be the dominating thing? It'd be x times x squared, so that'd give us x cubed. What would be dominating down here? X times x squared. That would be an x cubed. That would also dominate, which approaches 1. We need to check the other limit, just so we can get a habit of doing that. But the end behavior model would still be the same. It would still be x cubed over x cubed in terms of what dominates in the top and bottom in the negative direction, right? In the negative direction, these are still going to be our kings, which would still give us 1. So our horizontal asymptote is at y equals 1. All right. What about our vertical asymptotes? Vertical asymptotes, that's where just our denominator is going to be 0. So what x values are going to make only the denominator 0? Vertical asymptote here is that x equals -1. What about our removable discontinuities? Our removable discontinuity is going to happen where we'll have a 0 in the denominator and numerator. That looks like at x equals 2. At x equals 2, we'd have kill the denominator, make it 0. We would kill the numerator. This up here, when x is -3, if I asked about it, x equals -3 is a 0 of the function. Because when x is -3, it makes our function evaluate to 0. Didn't ask about that, though. Okay. One slightly trickier horizontal asymptote question, and then we'll wrap up with an FRQ. All right. What are all the horizontal asymptotes, so kind of giving us a hint here, of the graph of y equals 5 plus 2 to the x over 1 minus 2 to the x? Horizontal asymptotes. I've just reminded us that that means we need to take two limits. X approaches infinity. 1 minus, as x approaches infinity, of 5 plus 2 to the x over 1 minus 2 to the x. Sometimes you think you're talking out loud and you're just having thoughts in your head. All right, we need that limit. We also need the limit in the negative direction. All right, go ahead and pause the video and try both of these limits. See what you would get when we evaluate each of these limits. Alrighty, here we go, right? So the limit as x approaches infinity of 5 plus 2 to the x over 1 minus 2 to the x. Well, as x goes to positive infinity, what's going to dominate on top? Well, up top here, as x goes to positive infinity, 2 to the x is just going to keep growing. So it's going to definitely dominate over 5. It's going to stay small compared to 2 to the x as 2 to the x grows. And 1 minus 2 to the x is going to keep growing. So minus 2 to the x is going to dominate underneath. And that gives us -1 when we reduce. So one of our horizontal asymptotes seems to be y equals -1. So let's check the negative direction. Interesting stuff happens with exponential functions as x goes to negative infinity, though. 5 plus 2 to the negative infinity. Well, remember 2 to the negative x is going to be 1 over 2 to the x. So as x goes to negative infinity, I actually get 1 over 2 to the positive infinity. So 1 over 2 to the positive infinity, this is actually going to go to 0 as x grows, because it's going to turn it into a reciprocal 1 over 2 to the x as x goes to positive infinity. So actually 5 is going to dominate up top over there. As x goes to negative infinity down here, same thing. 2 to the negative infinity is going to be 1 over 2 to the infinity as x goes to positive infinity, which is going to go to 0, right? So this gives us 5 over 1. So our horizontal asymptote is at y equals 5. We have two horizontal asymptotes here, -1 and 5. All right. We're going to close out today with a free response question. I want you to kind of just watch and let me think through some things with you and fill in some notes, and we'll wrap up. All right. Let the function f be defined here. We got a piecewise function, a. We said, is f continuous at x equals 3? Explain why or why not. All right. We know if we're going to check continuity, we need to check three things. First, we need to make sure that the limit as x approaches 3 of f of x. I need to check that. So let me do that. That's relatively easy to check. I can say the square root of x plus 1. I can find that limit, the limit as x approaches 3. Square root of x plus 1, that'd be from the left side, right? Okay. That's going to give me, as x approaches 3, it's going to be 3 plus 1. That's the square root of 4, so that's 2. I can check my right-hand limit, the limit as x approaches 3 from the right. Check the right-hand side of this x equals 3 value. So that's 5 minus 3, which is going to give me a value of 1. That's not true. Why did I say that? That's weird. It gives me a value of 2. And so what do I know? I know that the limit as x approaches 3 of f of x exists. Great. I can even say and is 2. Okay, that's the first thing I need to check. I'm going to number it. The second thing I need to check So I checked the limit. The second thing I need to check is, does f of 2 exist? F of 2. Let me look up here my piecewise function. F of 2. Oh my gosh, I keep saying one thing, writing another. Or I keep saying the wrong thing. F of 3, because we're tracking continuity at 3. What is f of 3? F of 3, when I come up here, when x is 3, I would plug 3 into the square root of x plus 1. So that'd be the square root of 4, which is 2. So f of 3 exists. That's one of my criteria. And my third criteria is to show the limit as x approaches 3 of f of x equals f of 3, which I can do right away because I know the limit existent is 2. I know the point is 2, so I can simply say the limit as x approaches 3 of f of x equals f of 3, which is 2. And I'm basically done there. I guess if I want to make this a little stronger, I should probably add over here, just so they know I'm aware of this, that the limit as x approaches 3 from the left of f of x equals the limit as x approaches 3 from the right. From the right of f of x. All right. So what have I shown now? It does look like our function's continuous, so I can say yes, f is continuous at x equals 3 because the limit as x approaches 3 of f of x equals f of 3, which is 2, just to cover my bases. So you got 1 point for saying yes, it is continuous and equating the left and right hand limits, and then you got 1 point for your explanation involving limits. All right. So let's take a look at part B now. Slightly different question, one we've not really seen today. Find the average value. Find the average value of f of x on the closed interval 0 to 5. That's just a phrase we need to recognize, all right? The average value. The average value of a function f of x on 0 to 5. I would just write out the general expression for that. When we see average value, that is one of our formulas we need to remember. It's 1 over b minus a, the integral from a to b of f of x dx. Let's just write out what that would be, what they're describing here then. That'd be 1 over 5 minus 0, the integral from 0 to 5. That's an ugly looking 5. 0 to 5 of f of x dx. All right. That is what we need to actually evaluate here. But here's the problem I run into. F of x is a piecewise function, right? 0 to 3 and 3 to 5. We're kind of broken up. So I need to kind of fix this a little bit, right? Because the 1 over 5 part, that's fine. But my issue is going to be the integral from 0 to 5 is hard to take because it's broken up. But I know that I can add sections of integrals together. So what if I break this into the integral from 0 to 3 of f of x, that place where I have a breaking point there, plus the integral from 3 to 5 of f of x dx. That would give me the overall 0 to 5 integral, right? So that's what I'm going to need to do. You got 1 point for recognizing this. All right. So let's see what we can do. We need the integral. I'll kind of do this up here. I'm going to have to jump around a little bit. We need the integral then. We need the integral then of 0 to 3. From 0 to 3 of f of x dx. From 0 to 3, it's going to follow x plus 1 to the half power, right? dx. So let me take the antiderivative of that. That'll give me x plus 1 to the 3 halves, but then divide by my new exponent, so that'll give me 2/3 evaluated from 0 to 3. So that's going to give me 2/3 times, I'm going to plug in 3, 2/3, 4 to the 3 halves, minus 2/3. When I plug in 0, I get 1 to the 3 halves. So the 3 halves power of 4, the square root of 4 is 2. Cubed is going to give me 8. Times 2 is 16 divided by 3, so that's 16/3. Minus 1 to the 3 halves is just 1 minus 2/3. Remember, you don't actually have to simplify anything. If you just want to leave a bunch of numbers, that's fine as well in these values. That's okay. In this case, this comes out to be 14/3. So you could have just left things like this and used it down here when we get over to that spot. All right. I also need then to find the integral from 3 to 5. All right. The integral from, not 0, from 3 to 5. The integral from 3 to 5 of f of x dx. From 3 to 5, it follows 5 minus x dx, which is, when I take the antiderivative, 5x minus half x squared, evaluated from 3 to 5. So what is this going to give us? It's going to give us, when I plug in 5, that's going to give me 25 minus, plug in 5, 25 halves. Minus what I get when I plug in 3, which is going to give me 15. Minus what I get when I plug in 3 is going to be 9 halves. So this is going to give me 25 minus 15, which gives me 10. And I'm going to get minus 25 halves plus 9 halves, which is 10 minus, when I add 9 halves, that'll give me 16 halves. So that's going to be 10 minus 8, which gives me 2, right? Again, you don't actually have to simplify all this stuff down. You could have used what we're about to do. This 2/3 4 to the 3 halves minus 2/3 1 to the 3 halves, and then this whole expression down here, and just plugged it in over here. That would have been fine. In fact, that's probably what I would recommend doing to avoid any problems. And actually just write out that my average value is 1/5, and then simply say 1/5 of 2/3 4 times 4 to the 3 halves minus 2/3 times 1 to the 3 halves plus everything I got over here, 25 minus 25 halves minus 15 minus 9 halves. And just actually leave this as my final answer, because this is fine. I did the integral value, it's whatever that is. Plus, I did my integral value, it's whatever that is. And just leaving it like this would be my recommendation. If you are going to boil it all down and use the simplified stuff we did, you would have 1/5. We found that'd be 1/5 of 14/3 plus 2, which I'll call 6/3, which is going to give us, when I do 4 plus 6, it'll be 1/5 of 20/3. Which is going to give, when we reduce that, 4/3 as my average. All right, you got 1 point for your antiderivative of your square root. You got 1 point for your antiderivative of 5 minus x. You got 1 point for setting up this expression over here. And you got 1 point for your evaluation and answer. All right, let's take a look at our last part, part C. Suppose the function g is defined by this other piecewise function. K and m are constants. If g is differentiable, new word we've not seen today, at x equals d, what are the values of k and m? So differentiability, this is a good reminder, and we'll write some things down below as well. If something's going to be differentiable, we need to make sure it's continuous. We also need to make sure that it's what we call smooth, that we don't have a corner or cusp. To check that, essentially what we need to check is to make sure that the derivative is continuous. All right, so let's do that in this case. Checking continuity is not too bad. We want to find what are the values of k and m though. Well, if we're going to check continuity, if this is going to be true, then k times the square root of x plus 1 has to be equal to mx plus 2, right? When x is 3. Because if the function is going to be continuous, when x is 3, we're going to need the left and right side to be together and be equal to each other. So the limit exists, and they have a point there, and they're all equal. So if I plug in 3, for x, I get the square root of 4, so that gives me 2k. Plus, when I plug in 3 there, I get 3m plus 2. But I can't really solve for k or m there. So let me go over to my differentiability part, my derivative part of this. Let me take the derivative then up here, okay? I need the derivative of k times the square root of x plus 1. So that would be, when I bring down the half power, that'd be half times k times x plus 1 to the negative half power, right? Equals, when I take the derivative of mx plus 2, derivative of mx would just give me m plus 2, 0. So there we go. Now I want to check this at x equals 3. Again, I just took the derivative of both of these. If you need to write those out, that's fine. I plug in 3 now, and I would end up with half k, and then I'd have 4 to the negative half power equals m. 4 to the negative half. So that's 1 over the square root of 4. So that's 1 over 2. So this is 1 half k times 1 half equals m. So that's 1/4 k equals m. So k has to equal 4m. Why is this useful for us? Well, now I have two different equations over here, and I can substitute that k is 4m over here. So if k is 4m, over here means 2 times 4m, so that gives me 8m, because k is 4m. 8m equals 3m plus 2. Subtracting 3m, I would get 5m equals 2, so m equals 2/5. All right, so now I've solved for m. I now need to get what k is, right? I now know that m, though, is 2/5, so k then is going to be 4 times 2/5. So k is going to be 8/5. K is going to be 8/5. Point-wise here, you got 1 point for getting down to this spot here, knowing that 2k is equal to 3m plus 2. You get 1 point for solving for k or m in terms of a variable, and then 1 point for the values of k, which is 8/5, and m, which is 2/5. All right. There you go. Hopefully that gives you some insight into that free response question. I want to just fill in one thing at the bottom as a reminder about two of the concepts that are there. We need to remember our average value formula. The average value on the interval a to b of some function is 1 over b minus a, the integral from a to b of f of x dx. If you ever see that average value phrase, just write this out for that function and that situation, and it'll be a step into what you need to do. Okay, and for differentiability, we need to make sure that the function is continuous and smooth, quote unquote. And if the function is going to be smooth, we need to make sure that the derivatives, just like we checked, that the derivatives are continuous so that they flow into each other. So we took the derivatives and set them equal to each other. All right. Essentially what this eliminates is no cusps, corners, vertical tangent lines, and discontinuities. All right. Please make sure for homework you do a couple things. One, please make sure that you do the problems in the homework section. As we have started to do, there will be a score reporting thing you have to do. So you need to make sure that you do the free response question, score yourself, watch my video, do the multiple choice questions, score yourself, and then fill out the score reporting form, please. Please make sure you also take the Maclaurin series quiz today. Have a great day, everybody. I'm going to be trying to tone down the review stuff so it's a little shorter. I'm sorry today still went a little on the long side. I'm going to be working on breaking these things down. Please make sure you come back on Friday for announcements. There's going to be some important announcements for over spring break. Bye, everybody.